there's room in here. Just enough for two in here.
So what we're going to look at are first order. So meaning that the highest derivative is the first derivative, right? So first order autonomous equation has the form of the following. So this is what it looks like. Is an example would be x prime is equal to some function of x alone, okay? So in this case, our x prime, our first derivative, doesn't depend on t, because we don't see any t's here, right? It's not f of t comma x, it's just f of x, that's all. So that means that the slope, which is given by the first derivative, right? So the slope at any point depends only on x, not t at all. Not t at all. Okay? Which gives us a graph something like this. So here's an example. Here's a little like mini example. So let's say y prime is equal to y. So let's say we have our ty graph here. Ty. And let me extend this down a little bit. Okay, so let's say here's 1, 2, 1, 2. Right? And then, so what this means is that y prime, so our slope when our y is equal to 0, it's just going to be straight across, right? So we'll have horizontal lines here. Okay, when y is equal to 1, then our slope is equal to 1. So something like that. When y is equal to 2, our slope gets a little bit steeper, okay? And then on the other side, when our y is equal to -1, let's say, then we have negative slopes. And when y is equal to -2, we have steeper negative slopes. Okay, so it looks something like that, where the slopes remain constant all the way across when you're at a certain y value, when you have a fixed y value. It doesn't depend on t, okay? The only thing that does depend on t is when you do have like a specific like initial condition, and then you can pin down an exact point and figure out which curve you're actually looking at. But right now we're not going to be doing that, okay? So in doing this, when we have our x prime is equal to f of x, so let's say something general, right? So this is our general like autonomous equation. What we can do is actually study like qualitatively as opposed to like actually explicitly finding a solution or whatever, our x of t or something like that, and then solving there and looking at its behavior. But in this case, what we're going to do with autonomous equations is study qualitatively the behavior of our solutions to this autonomous equation without explicitly finding those solutions, okay? And I'll show you how on the following slides. So the first thing to note where we can start is what's called equilibrium points and solutions. Equilibrium points and solutions, okay? So we kind of already ran into this a little bit on in section 2.7 when we were doing existence and uniqueness of solutions. Remember when we would find some, it would be pretty easy to find some solutions to an ODE just by looking at what makes our x prime or y prime equal to 0. Right? So let's say our x prime is equal to f of x. Okay, well, we're just speaking very generally here. So let's say x naught is an equilibrium point. So x naught is an equilibrium, I'll just abbreviate, equilibrium point. That's the terminology used for it. So is an equilibrium point if f of x naught, which is equal to x prime, is equal to 0. So if it makes our x prime equal to 0, then that means that this x naught value is an equilibrium point, okay? Whereas there's just a tiny difference here. So if you have x of t is equal to this constant value, you could say like it's a 2 or something like that, then this equation here is called an equilibrium solution. Equilibrium solution, okay? All right, so this is a constant function, just by the way. Constant function, because our x naught is a constant. So this is a constant function, okay? So for example, just a quick example here, on our previous example there, where we had y prime is equal to y, and remember on the t-axis, so this is y and this is t, we actually had these horizontal lines, right? And then we had everything like this, and like that, etc., okay? So we had something like this, and then they went steeper and steeper and steeper. This thing here, this whole line, this y of t is equal to 0, this is an equilibrium solution, right? Because this means that at all of these points, no matter what t is, our y prime, our slope at each of these points is equal to 0, which means it's horizontal, okay? So this is an equilibrium solution. Okay, so now that we've established what an equilibrium solution is, let's go a little bit further and analyze our y prime of fy, let's say. So our autonomous equation here. Let's say, I think it's optimum to walk through an actual example to see like what we would actually do in this case. So let's say we have this as our function, okay, which we can actually split that up into y plus 1 and y minus 1, that one here, and then we have our y minus 2. Okay, so in looking at this is an autonomous equation, right, because we don't see any t's popping up or any independent variables, right? We just have our function variable and the first derivative of our function. Okay, so what are our equilibrium points or our solutions? Our equilibrium solutions would be y of t is equal to -1, as well as y of t is equal to a +1, as well as y of t is equal to +2. Okay, so those would be our equilibrium solutions. And on our graph, what we're actually going to do is the first graph we're going to make, because we'll actually be making, for each of these problems, we'll make 2 different graphs, okay? The first one is y versus y prime, or y prime, that is, y prime, which is equal to our f of y, versus y. And then another graph will be, if I can draw a straight line here, hold on. And then our other graph will be our y versus t, okay? So that'll be later on though, okay? We'll do the second one later. Alrighty, so let's look at this one. So we have something like this, and let me draw in some values here. So we have -2 going on, as well as a +2, and a +2 here, and a -2. Okay, so what is actually going on? So we have y prime is equal to basically 0 when we have y is equal to -1, 1, and 2. So these are basically the roots of this function here. Okay, so we have at -1, we have 0. All right, at +1, we have a 0. At 2, we have a 0. Okay, and then if we just graph this function overall, our f of y, this is going to be a positive cubic, right? So that means it'll be like an S kind of thing. So it'll go up, above, come down, and go back up. Okay, so it crosses the y-axis 3 times because we have 3 roots here. Okay, so now here's the important thing. This thing here is going to be called our phase line. The y-axis here is called our phase line. Okay, that's just the term given to it. Okay, and then what we have to do is study. Okay, so let's see what's the relationship between our y prime and our y. Okay, so here up to -1, we have that our y prime is negative, right? So what does that mean? When our y prime is negative, that means the slope is negative, which means that our y value, our function, is decreasing, okay? So I'm just going to write decreasing down here. So that means that our y, which is this axis, is going this way. It's decreasing. Okay, so there's that arrow there. Now let's look at this interval, -1 up to 1. Then we have that our function, our f of y, which is y prime, which tells us our slope at any given point, then that's positive, which means that our function must be increasing, meaning that our y is increasing. So now it's pointing this way on this interval here, okay? And then when we go down here, this part is decreasing a little bit, that little tiny interval in between 1 and 2, and our arrow then points to the left, where y is decreasing. It's going down, okay? And lastly, this last interval is increasing because our y prime is positive. That means that our y must be going toward the positive values, okay? Or greater values there. Alrighty, so let me redraw this on the next slide so we can see a little bit clearer version of it.